Hey everyone, welcome to University of Winnipeg Chemistry 1112. This is Dr. Carroll here. We're looking at Chapter 15 today, Aqueous Acid-Base Equilibria. So in your textbook, we are on page 725, Olmsted, 3rd edition, and you have seen acid-base before. In fact, if you go to this YouTube link, tinyurl.com/chemu6s1. That's a grade 12 review. It's 54 minutes. You can watch it at 2 times. You don't have to watch it, but watching it prevents me from having to, allows me not to have to go over the naming of the different kinds of acids and some of that other stuff. So watch it if you want. Watch it at 2 times speed for extra fun. Okay, so I'll wait. Okay, we're back. So now let's get to the good stuff here, and there will be some review anyways. So we're going to learn about the fact that acids donate protons to bases. If we're talking about the Brownsted-Lowry theory of acids and bases, I sometimes call that the BL. These are two guys who are both credited with the definition for acid-base in terms of Brownsted-Lowry in the tinyurl.com that you listened to before. You heard, I think someone's drilling outside with a jackhammer. That's great. It is outside. Okay, well, I'm just going to ignore that and keep going. That is areneous acid base, mineral acids, diprotic, polyprotic, polypocket, all this stuff. We're going to get to that. We're going to talk about pH related to concentrations. We're going to, look, we do a bit of the naming and talk about the strengths of acids and other good stuff. So, again, lots of this we've seen before. So here we have in the Brownsted-Lowry definition, there's an HCl, and it is throwing a proton to H2O. So HCl is the Brownsted-Lowry acid. H2O is the Brownsted-Lowry base. That pen is too thick. Let's send it down there. H2O is a Brownsted-Lowry acid. And then if you go the other way, H3O plus, no, H2O is a Brownsted-Lowry base. It's accepting a proton from HCl, right? Going the other way, H3O plus is a Brownsted-Lowry acid, and Cl minus is a Brownsted-Lowry base. So we will learn that HCl is a strong acid, or if you watched that 54-minute review, you know that to be the case. So this reaction from right to left really doesn't happen, because as soon as you would form an HCl, it'll zoom back to Cl minus. We say, and you've seen this before, HCl and Cl minus are conjugate acid-base pair. That's one conjugate acid-base pair. They differ by a proton. So another way to do right is the slash notation. You put the acid and then the conjugate base. And H3O plus and H2O is another conjugate acid-base pair. Put the acid first and then the base. So when you have two things combining to form two other things, well, you have two conjugate acid-base pairs. Here is PO4 3- reacting with water. Water is an interesting thing. It can act as an acid or a base. Amphiprotic is if we're talking about specifically Brownsted-Lowry acid-base chemistry. Water is said to be amphiprotic. It can gain a proton or lose a proton. In general, water acidic or basic properties is called amphoteric. So that's another word you sometimes hear. But amphiprotic is better because it's specific for Brownsted-Lowry acid base. So here you have PO4 3-, the phosphate anion. Well, it cannot lose a proton. It can't give a proton to something because it ain't got no proton, right? Sounds like a song. Ain't got no protons. But it can accept a proton from water. So PO4 3- is a Brownsted-Lowry base. H2O is a Brownsted-Lowry acid. So HPO4 2- is a bronzed acid, and OH minus is the bronzed base. So we got H2O and OH minus is one conjugate acid-base pair, and PO4 3 minus HPO4 2 minus is another conjugate acid-base pair. Okay, so we have H2O is an acid and its conjugate base is OH minus. HPO4 2 minus is an acid and its conjugate base is PO4 3 minus. Which way is favored in a system? It's favored going from strong to weak, and we're going to get to that a little later. There's some pictures of it. I seem to remember there being some typos in some of these pictures, so I'm not going to even bother looking at them. I'm going to go straight to another example. Here's acetic acid, classic. Acetic acid, sometimes they write as HAC. Some people write it as CH3CO2H. The formula is C2H4O2. That's not going to be very helpful in our descriptions. A condensed organic chemistry kind of thing like this is good. So that's an acid. It here is reacting with hydroxide in this example. So OH minus is the base. Sometimes it's written like this: acid 1, base 2, and then going the other way, the conjugates, base 1, acid 2. And then you put these little guidelines with base 2 and acid 2, and acid 1 and base 1. So your conjugates, you got CH3, CO2H with CH3, CO2 minus, and H2O and OH minus. If we draw this out, so you got CH3, C double bond O, OH, plus OH minus, and this is the acidic hydrogen. This one gets shot over to give you H2O plus CH3, CO, O minus. Okay, it's right here. You got the electronegativity differences is greater. Carbon and hydrogen, as we talked about before, the polarity of these, it's very small. Electronegativity difference is small, so we say that is essentially nonpolar end, that methyl group. But the hydrogen bonded to the oxygen is almost a proton already, so it's the one that snaps off. We call it the acidic hydrogen, and so there you have it. And here we have another conjugate acid base, HF and H2O, and I've already talked about this. So let's jump straight to an example here. Write the chemical formula and Lewis structure, draw a molecular picture. Conjugate acid of ammonia. So you add an H plus, exactly one H plus, and you get NH4 plus. So there it is. That's the conjugate acid. Conjugate base of formic acid, that's formate. That's HCOO minus. So there it is. Conjugate acid of hydrogen sulfate, HSO4 minus. So I add an H plus, exactly one H plus, and I get H2SO4. Okay? And there it is. Let's try this practice exercise. Dihydrogen phosphate. Well, let's just look at the whole thing here, this series here. H3PO4, its conjugate acid is H2PO4 minus. You can have H2PO4 minus, depending what it reacts with. It can gain a proton and go back to H3PO4, or it can lose a proton and go to HPO4 2 minus. And HPO4 2 minus can do that same thing, gain a proton or lose a proton, so you can get PO4 3 minus. Now you can't go any farther than that. Okay? So the conjugate acid of H2PO4 minus is H3PO4. The conjugate base of H2PO4 minus is HPO4 2 minus. HPO4 2 minus's conjugate acid is H2PO4 minus. Its conjugate base is PO4 3 minus. If I put in PO4 3 minus and try to get its conjugate base, well, that's not applicable. There isn't any, so forget about it. Can't lose a proton. Okay, so conjugate acid bases, Brown-Stillari acid base, some of those other characteristics you saw by rewatching that grade 12 screencast that I mentioned at the beginning of this one. Autohydrolysis of water is sometimes called autoionization of water. Water all by its lonesome can break apart a bit into H plus and OH minus. And so here we see it's 2H2O goes to OH minus plus H3O plus. Another quicker way to write it is just H2O goes to H plus plus OH minus. I like to write it like that. I know that H3O plus and H plus essentially are the same thing. It's just water around H plus to give you H3O plus. It's like a solvated proton. And it's just faster to write this, but the book sometimes does that, sometimes doesn't. So the equilibrium constant is given a special name Kw, and at 25 degrees Celsius, Kw, the water autoionization constant or water hydrolysis constant or autohydrolysis constant is 1 by 10 to the minus 14, which means at 25 degrees Celsius, the concentration of the hydronium equals the concentration of the OH minus equals 1 by 10 to the minus 7 molar. So in pure distilled water, if you don't have any like metal ions or anions other than hydroxide dancing around, this is the concentrations of each. They're going to be equal. If I have an acidic environment, I'm going to have an H3O plus greater than 10 to the minus 7 and an OH minus less. And if I have a basic solution, then the OH minus concentration is going to be greater than 10 to the minus 7. The product always has to equal 10 to the minus 14. Okay? And that should bring back some good memories. Here we see one of the protons is going here, and you're left with hydroxide and an H3O plus. Okay? If the water is neither acidic nor basic, we say it's neutral. If you have more H plus than OH minus, it's an acidic. I just said less H plus than OH minus is basic. If it's acidic, we recall that the pH is less than 7, the pOH is greater than 7. If it's basic, the pH is greater than 7, the pOH is less than 7. And it turns out that the pH plus pOH equals 14. I'm going to do calculations like that very soon. Okay. Any questions? Send me an EDSB or an email or a Gmail. So, strong acids, there's only 6 most common ones, and they're the ones which give the proton away essentially 100%. So there's no intact, unionized molecules remaining. Most acids are not strong, most are weak. But here's 6 strong ones which are all important. HNO3, HClO4, H2SO4, the first ionization, not the second. We'll get into that a little later. HCl, HBr, and HI. So those ones you should essentially memorize. You don't want to memorize the weak 900,000 of them. You'd rather memorize the 6 strong one. HF is not a strong acid, by the way. You think, oh, maybe it should be because HCl, HBr, and HI are. But no, it's not. And it has to do with the bond energy between the H and the F. And we'll see examples of HF in this chapter. So because they're strong acids, whatever your concentration of the acid is will be the same as your concentration of the hydronium, except for that H2SO4 one. That one's got to get to that one a bit. So let's look at an example here. Determine the ion concentrations of 5 by 10 to the minus 2 molar HClO4. Well, I just write it like this. The book's being fancier, but at equilibrium, I've lost all the HClO4, so my H3O plus is 5 by 10 to the minus 2 molar. Not minus 12. 5 by 10 to the minus 2 molar. My perchlorate anion is also 5 by 10 to the minus 2 molar. Now I do have hydroxide here, even though it's not explicitly shown, but everything's dissolved in water. So my hydroxide is my Kw, 1 by 10 to minus 14, divided by my H plus, or H3O plus, 5 by 10 to minus 2. So I do have hydroxide. So I'm going to take, what's this calculator not working again? Gotta smack it a few times, this one. Oh, heck. Why does it not work anymore? Really? Okay, so I'm going to run and get my cell phone calculator, which is pretty good. Five by 10 to the minus 14. Okay, 1 second. Where is that? I keep pressing the button on this one because I know it worked just a while ago. Maybe if I put it in a different way in the case. No, okay, 1 second. Oh, better take off the headphones. I forgot what the pause button was on this screencast. So I'm going to go into extras. I'm going to look for the calc EQ7. Oh, that's a good calculator if you need one. So somebody's saying, oh, yeah, I could do that in my head. Yeah, sure. 1 by 10 to the negative 14 divided by 5 by 10 to the negative 2 is 2 by 10 to the minus 13. So there we go. Okay, that wasn't even asked for in the question, but it's good now that I know about calculators for questions where we'll need it. Okay, so, oh my goodness, look at this mess they do. It just get to the right answer. They're going to talk about the hydrolysis of water. They just make it way more complicated. Determine the ion concentration of a solution of HCl of concentration 6.5. Now here's one we may not see before, millimole. That one actually comes in handy in acid-base chemistry. So that's 6.5 by 10 to minus 3 moles per liter, millimole. So at equilibrium, my H plus will be 6.5 by 10 to minus 3 molar. My Cl minus will be 6.5 by 10 to minus 3 molar, and my OH minus will be Kw. So 1 by 10 to minus 14, let's clear this. 1 by 10 to the negative 14. 1 by 10 to the negative 14 divided by 6.5 by 10 to the negative 3. And I get 1.54 by 10 to the minus 12. Okay, let's clear that. Okay, oh, I can check my eBay purchases on the fly here. Okay, strong bases, the alkali metal hydroxides, and what else? Most alkaline earth metal hydroxides are strong bases. All these things with nitrogen derivatives of ammonia are weak bases. Those are very common. Those are the ones we'll use most with the weak bases. But a strong base breaks apart into the cation, which just swims around doing nothing, really, and the hydroxide. That's where the action is. Okay? So let's jump straight to an example here. What are the ion concentrations in 0.5 liters of an aqueous solution that contains 5 grams of ammonia? So the molar mass of ammonia is 40 grams per mole. You might remember for molar masses, there's a nice molar mass calculator and a calculator for lots of other good things in chemistry and physics too. tinyurl.com. URL, Uniform Resource Locator, Calc VMC. So that's a good one to use if you don't always want to go to the periodic table. So the molar mass of NaOH is 40. The moles of NaOH is 5 grams over 40 grams per mole. So 0.125 moles. And then the concentration of NaOH is my moles, 0.125 moles, divided by 0.5 liters. And you get 0.25 moles per liter. And so then my Na plus and my OH minus are both 0.25 molar. And my H3O plus is, again, they make all this big fuss about the initial water before. Don't worry about that. Just jump straight to the answer. It's Kw over OH minus, 4 by 10 to minus 14. Okay, let's try another one here. Lithium hydroxide, so 68 milligrams, so that's 68 by 10 to the minus 3 grams in 125 mils, so that's 0.125 liters. So now I got to get the molar mass of lithium hydroxide. Now I could go and show off using that molar mass calculator. Why don't I just use the periodic table? So oxygen and hydrogen, it makes 17. Lithium is roughly 7, so that's 24, or 23.9. Let's make it 24 grams per liter. So 68 by 10 to the minus 3. Oh, I don't want to be in power saving mode. 68 by 10 to the negative 3 divided by 24, and all that divided by 0.125 is 0.023 molar. So the lithium plus is 0.023 molar, and the OH minus is also 0.023 molar. And practice exercise 15.3, I guess I should look at the answer there. Oh, I meant to write that down. That's okay. Gives you a chance to try it. Go to check your eBay purchases. And 0.023, and then my H3O plus is Kw, 1 by 10 to the negative 14 divided by answer from before. 4.4 by 10 to the minus 13. Oh, that's neat. You can use that answer thing there. 4.4 by 10 to the minus 13. So H plus, or if you'd rather write H3O plus, it equals 4.4 by 10 to the minus 13 molar. Okay, so that's good. And you see that there's a lot more OH minus than H plus, which there has to be. Here's a quick question, section exercise. What's the OH minus in a sample of acid rain? So acid rain has an H plus more than 10 to the minus 7. So OH minus would be Kw 1 by 10 to the minus 14 divided by H plus 2.5 by 10 to the minus 4. 1 by 10, oh, clear. 1 by 10 to the negative 14 divided by 2.5 by 10 to the negative 4, and I get 4 by 10 to the minus 11. Okay, you can try 15.1.3 on your own. 15.1.4, identify the conjugate acid and base of HCO3 minus. So H2CO3 is the conjugate acid, and CO3 2 minus is the conjugate base. HSO4 minus, the conjugate acid, is H2SO4. The conjugate base is SO4 2 minus. Okay. Well, we can certainly do 15.2 in this screencast, since this is review pH scale. One thing about pH that you should remember is you can have pH is less than 0 and pH is greater than 14. P means the potential of hydrogen. That's the way the word came from. But the P function, P just means -1 times the log of something. So we're going to talk about pH, which is -1 times the log of the H plus concentration, or H3O plus concentration. POH, which is -1 times the log to the base 10. This is one of the few times in chemistry where we use log to the base 10 rather than natural log. pKa is -1 times the log of Ka, where Ka is the acid ionization constant. And pKb is -1 times the log of Kb, where Kb is the base ionization constant. Okay, and I wonder how I'm going to use log on this calculator. Well, we'll find out. So here we have 6 molar HCl, so the pH of 6 molar. How do I do it on this calculator? Let's clear. Maybe I hit log first and then 6, log of 6 equals 0.77, but it's negative, so it's negative 0.78 actually. Pure H2O, the pH is going to be 7 because it's going to be the log of 1 by 10 to the -7, and then multiplied by -1, so it's 7. pH of H3O plus is going to be a lot higher than 7, because I'm going to take, let's clear that, log of 4 by 10 to the -14, and I get -13.40. Typically we give, oh no, but it's times that, so it's positive 13.40. Typically we give pHs, POHs, pKas, pKbs in units of, or to 2 decimal places. Okay. I like to put the -1 times the log rather than just a minus log, but that's okay. pH 7 defines neutral solutions. More acidic has a lower pH. Because it is a logarithmic scale, a change in pH reflects a 10-fold change. So if I have lemon juice is 2, acid rain has a pH of 4, then the lemon juice is 100 times more acidic. This little formula I made up, 10 to the, I don't think I made it up, but I use it, 10 to the change in the pH between the two solutions tells me how much more acidic one is than the other. Okay, so a pH change of 1 doesn't mean a change in concentration of 1. It means a change in concentration of 10. It's a log to the base 10 scale. pH was developed by some guy, Soren Sorensen, who was a brewmaster, and he was looking at how come some enzymes will ferment the grains used to make alcohol in better conditions than others. So because enzymes are having their activity change depending on the acidity. Okay, so you have a big range of concentrations, much more than 1 molar to much, or greater than 1 molar to less than 10 to the minus 14. So it's much more convenient to have a pH range. Okay. And here we see some pictures of some typical acids and bases in terms of their pH. So sodium hydroxide, ammonia, milk of magnesia, which is magnesium hydroxide, detergents, which have bleaches in them. Those are basic. Baking soda is basic. Human blood slightly basic. Then we have milk, because of its lactic acid, is slightly acidic. Even just natural rainwater. Its pH is 5.5 because it's got carbon dioxide dissolved in water, which gives you carbonic acid. So vinegar, lemon juice, stomach acid, which is really buffered hydrochloric acid, and then there's concentrated hydrochloric acid. You can determine pHs, old school, pH paper, and you match what you dip into this color system. Some of you may use similar things like this with swimming pool maintenance. And then there's pH probes, which is the way if you get a chance to do a lab, you would do that. So if you're given the pH, then you can get the H plus. So H plus is 10 to the minus pH, right? Because I take the inverse log of both sides, which multiply both sides by -1, then take the inverse log. So pH is 3.05, so the H plus in this example will be 10 to the minus 3.05. I wonder how I do that on this calculator. Let's clear it. So I want to take inverse log. I got log here. I got 10 to the x. Oh, fiddly darn. Okay, I wonder if I take second log. Second log. Oh, it just says log again. What if I take second? Oh, a whole new set, a whole new ball game appeared there. D by dx. Oh my goodness, we got all sorts of things. Oh, there's the meaning of life button. Okay, no, so we're going to take 10 to the x. Oh, the dogs have returned. 10 to the negative 3.05. And I end up with 8.91 by 10 to minus 4. So that is my concentration of the H plus. And once I got that, then I can get the OH minus, because it's just Kw, 1 by 10 to the minus 14, divided by the H plus, or HVO plus, 8.91 by 10 to the minus 4. So let's go back to 1. Where's my EXP button? 1 by 10 to the minus 14 divided by, I don't know what the dog is wailing, 8.91 by 10 to the minus 4, and I get 1.12 by 10 to the minus 11 molar. You should always check when you multiply the OH minus and the H plus. When they multiply together, they better give you 10 to the minus 14. So 1.12 by 10 to the minus 11 times 8.91 by 10 to the minus 4, and I get 1 by 10 to the minus 14. So that's good. Another way to do this, because pH plus pOH always equals 14, so if I know the pH is 3.05, then the pOH is 14 minus 3.05, which is 10.95, and then my OH minus is 10 to the minus 10.95. So that's another way to do that. Second here. 10 raised to the minus 10.95. And I get 1.12 by 10 to the minus 11. Hooray! Okay. The book makes it more complicated. Okay, let's try practice exercise 15.4. Milk of magnesia. You have an aqueous suspension of magnesium hydroxide. The pH is 10.5. Okay, so that means that my pOH, I like to get the pOH as soon as I can because it's an easy math, right? I don't even need this fancy calculator. It's just 3.5, right? So my H plus is 10 to the minus 10.5, and my OH minus is 10 to the minus 3.5. So let's clear this. 10 to the minus 10.5, 3.16 by 10 to the minus 11. And my OH minus, is this where the pen stopped working again? That's usually a signal. 3.16 by 10 to the minus 11, and the OH minus is going to turn out to be, actually I can do some on the paint there. This is practice exercise 15.4, 3 by 10 to the minus 4. Okay. Here's the proof that pH and POH gives you 14. We have KW. Okay, you can just see the arrow there, right? KW is H3O plus times OH minus. Take the log of both sides. So the log of KW is the log of 1 by 10 to the minus 14. And the log of a product is the sum of the logs of the terms giving you the product. So log of H3O plus plus, log of OH minus, log of 10 to the minus 14 is negative 14. Multiply both sides by negative 1. And you get pH is negative log of H3O plus, POH is negative log of OH minus. Add them together, and you get 14. Okay, so we can look, what's the pH of a 0.25 molar solution of NaOH? So let's get the OH minus concentration. It's a strong base, so the OH minus concentration is 0.25. And then the POH is the negative log of 0.25, which turns out to be 0.6. And my pH is 14 minus that, which is 13.4. Okay, and these are the questions where they try to trip you up, because in a multiple choice, all these answers will be in there. And then you say, well, wait, are they asking for pH or POH? And they're asking for the pH, so it's 13.4. And then I could get H3O plus is 10 to the minus 13.4, which is 4 by 10 to the minus 14 molar. Okay. Let's try the second exercise, and then that will be good for the first screencast, because this pen's not working, and then we'll do weak acids and bases in our second one. So let's go to the yeah, it works here. So this is on page I'm into chapter KA. No, not there yet. Page 735, 15.21. Page 735, 15.2.1. So we say determine the pH of 1.5 by 10 to the minus 3 molar HCl. Well, let's find everything we can about it, okay? So HCl goes to H plus Cl minus. If you're interested, just thinking about the future, my Ka is H plus times Cl minus over HCl, which is a huge number because we don't have much HCl anymore at equilibrium. It's strong acid, so it's almost all broken apart. The HCl was 1.5 by 10 to the minus 3, so my H plus is 1.5 by 10 to the minus 3, and my Cl minus is also 1.5 by 10 to the minus 3. Those are moles per liter. So my pH is the negative log of 1.5 by 10 to the minus 3. My POH, hydroxide, which is there by virtue of it being aqueous, is 14 minus the pH. And so let's get this pH. Okay, now somehow I'm in my Discord channel now. So I'm going to take the log. Where the heck is it? First. There you go. The log of 1.5 by 10 to the negative 3 times negative 1. Oh, I did that in my head. 2.82. And it's good to realize that the pH is less than 7. If we're talking about hydrochloric acid, we would expect the pH to be less than 7. So the pH is 14 minus 2.82. 14 minus 2.82. Which is 11.18. And my OH minus concentration, I could do it two ways. I could do it KW or H plus, or I could just do 10 to the minus 11.18, which is the same thing as kW over my H plus. And if you have time, you do it both ways. So 1 by 10 to the negative 14 divided by 1.5 by 10 to the negative 3, and I get 6.67 by 10 to the minus 12. And then you check and you multiply that times 1.5 by 10 to the minus 3. Oops, no. 6.67 by 10 to the negative 12 times 1.5 by 10 to the negative 3. 1 by 10 to the minus 14. So that's good. Now there's another part to it though. 2.5 by 10 to the minus 2 molar NaOH. So let's make a new. Okay, so NaOH goes to Na plus OH minus. So Kb is not really applicable. We use base ionization constant when we're talking about weak bases. 2.5 by 10 to the minus 2. So that's 0.025. 0.025. So we can do it different ways. I can get the H plus right away. It's Kw 1 by 10 to the minus 14 divided by 0.025. One by 10 to the negative 14 divided by 0.025, and I get 4 by 10 to the minus 13. Okay, so I got the H plus is 4 by 10 to the minus 13. I got the OH minus is 0.025. Now I can get the pH, and it's going to be more than 7 because we're talking about sodium hydroxide, which is a base. So 4 by 10 to the minus 13. Okay, I'm going to take the log of that answer, multiply by negative 1 in my head. Oh, fancy. So 12.40. And the POH is 14 minus that. Can I do that in my head? Sure I can. 1.60. 10, yeah, okay. And to check, I can take 0.025, the log of 0.025, multiplied by negative 1, and I get 1.6. Okay, so that's good for, which is mostly an introductory thing. We will get into 15.3 in our next lecture.